Hey everyone, so let's start with a bit of a reminder of what it is to be an x square. So an x square, again, is actually a story. It's a shape. It's an actual literal square. And we're going to be using this idea of shapes and squares and rectangles a lot in this class because it's a nice way to get our intuition involved in the mathematics. So imagine that I just had a whole bunch of groups. So here we have, I don't know how much is in each of my groups. It's an unknown amount of groups, but my logic can think of groups without having to know how many are in each group. They're just piles, or what I'm about to show you is that we could take those piles and stretch them out into rows. So imagine I have an unknown amount of things, like right here, this is just X things, right? I've got 1, 2, 3, 4, 5, and some amount all the way. Some amount, we'll just call that X. So here we have X in each row. And then what we're going to talk about is that below that, I'm just going to have X groups of that. So that means that there are X rows, 1, 2, 3, 4, X, an unknown amount of rows, but the same amount of columns. I don't know how many that is, but we're going to say it's the same amount. It's okay for me to think of that as a square because that's what it means to have something that is just groups of groups, is that I can organize it in a grid just like this. So we're going to call this entire thing just x squared. And to make our math easier moving forward, we're just going to be drawing squares if we want to be representing that as a picture. And just understand that within this is just x groups of x. Now, similarly, we could talk about just x as being just one of these rows. So like if I go in here and I just grab an unknown amount of things, then I can just put that below and I'll just call that x. That's now its own little rectangle. So I'll shade it in. And there you have now a group of x underneath it. So we have x squares, which is x groups of x, and then one group of x, which is just x. So I can do this, and then I could maybe put some more in here all over the place. Notice I could even do that going up and down. So in these tiny little squares here, I could just put in one object. And then on the next one, I could just put in one object. And we'll just say that how many do I have there? I have 2. And we can represent all of this using symbols, because obviously the pictures are really nice, but we may want to be able to talk about this faster and expand our intuition. So what is it that I have in all of this together? Well, in all of this together, what we have looked at now is x groups of x in this first square, and then the same thing in the second square and same thing in the third square. In fact, we could even just type that into everything. So there you have it. Now that's 3 of these x squares, and x square here, and x square here, and x square here. We have how many x's? 1, 2, 3, 4, 5, 6, 7 groups of just my unknown rectangles. So that would be 3x squares so far. I have 7 x's, and I have 2. So this is what we can work with whenever we're talking about distribution. This is literally distribution. It comes from having x and x and x and 1. In other words, x and x and x and 1. I could just think of this entire thing as 3 x's and a 1. And on the other side of the rectangle, we have x and 1 and 1, which means I have x and 2, which means 3x times x gets me 3x squares. And where does that appear? Right here. That's literally these 3x squares is what I mean when I say 3x squared. And then when we say 1 times x is one group of x, that's going to be just 1x. Where does that appear? Well, that appears right here off to the side. This is my 1x right here. And then I similarly have 6 x's that appear when I do 2 groups of 3 x's. That would be 6 x's. And 2 groups of 3 x's would be 1 group of 3 x's right here. That's 1 group of 3 x's. And then 2 groups of 3 x's. So that gets me 6 x's total. And then my 2 appear on the bottom right when I have 1 times 2 is 2. So this entire thing is just simply the result of a rectangle that's 3x and 1 for its length and x plus 2 for its width. In other words, I could represent this entire thing by a factoring, a moving from the amount of stuff I have in a pile to a discussion about those things in terms of groups. Because imagine if I didn't have this organized as a rectangle, and imagine I just had all these dots thrown into a pile with no organization. That's what this is saying, is that I just have an amount of stuff. I have a summation, I have a collection and an adding to a pile. This is us adding in our logic to say that not only is it a pile of stuff, it's a pile of stuff I can organize nicely in a grid. Now, the really interesting question becomes, are all quadratics able to be expressed this way? So in other words, if I gave you something like 3x squared plus 4x plus 1, could this be a rectangle? Would we have it so we could organize it in just the right amount of grids, columns, and rows? And if so, what does that rectangle look like? That's the interesting question for today's video. I want to talk about a method for factoring that's called the AC method. Now, this title means almost nothing until we explore some of the patterns that go into it, but instead of trying to memorize this method, I want to show you where it comes from, because it comes from something that's just absolutely beautiful. And if you take time to understand where it comes from, that's a lot less that you have to memorize, especially when you're worrying about trying to study for tests or whenever you're trying to get a lot of homework done. So first, let me just remind us of this pattern that we've been seeing as we've been looking through distribution. Remember that, for example, if I wanted to do something like, 3 plus 4 times 1 plus 2, that I could look at this through the mathematical model of a rectangle. Because whenever you have something that is being multiplied, we just simply have groups. That's what it means to multiply. It's like, for example, 2 times 5 means 2 groups of 5, or 5 groups of 2, which can be represented very easily as a rectangle. So whenever we have multiplication, I like to look at this entire thing as just length times width, because that's what it means to be multiplying, is just to be creating groups that I could organize in a rectangle. So for example, let's look at this one here. 3 plus 4 times 1 plus 2. Well, if I wanted to multiply all of this out, that means I have 3 and 4 groups of 1 and 2. But let's break that down a little bit more. 3 groups of 1 would be 1 group of 1, 2 groups of 1, 3 groups of 1. That would be 3 total, so this is going to be 3. If I have 1 group of 4, or 4 groups of 1, that's just going to be 4. And if I have 3 groups of 2, that would be 2, 4, and 6. Okay, that would be 6 here. And then 4 groups of 2 gets us 8. So all in all, I can look at everything that we just had as either 3 plus 4 times 1 plus 2, or I could look at that as 3 and 4 and 6 and 8. Everything that I create from it, which gets me what? 7 plus 14, or 21. And if this feels a little bit weird, feel free to do some simplification in another way, because 3 plus 4, after all, is 7, 1 plus 2 is 3, and 7 times 3 is also 21. So there are many different ways to look at this, but I love the idea of looking at multiplication as creating a rectangle. Now, why is this so interesting for me? Because what happens in this pattern also has a hidden pattern within it, and this is where mathematics really allows us to see some fantastic ideas. Do y'all notice what happens if I was to say, look at these two numbers as together, and if I was to look at these two numbers together? Do we see a pattern that jumps out to us? 6 and 4 compared to 3 and 8. Maybe not? Okay, well, let's take a moment and let's do another example of distribution, and we'll see if these patterns emerge. Let's now do, let's do 2x plus 3 times 4x minus 1. So that would be 2x plus 3 as the side of a rectangle, and 4x minus 1 as the side of a rectangle. Multiplying this out makes doing this foiling or distribution super easy. This would be 8x squared, because it'd be 2x times 4x. 3 times 4x would be 3 groups of 4x's. So like 3 groups of 4 apples would be 12 apples. This will be 12 x's. And 2x times negative 1 means the opposite of one group of 2x. So that would be negative 2x. And 3 times negative 1 would be the opposite of a group of 3. So negative 3. And if you, again, highlight here and here, you will see that there is a pattern that is emerging. Do you see it yet? Think about it through the lens of multiplication. 3 times 8 is going to be 24, and 6 times 4 is also 24. In fact, this is a pattern that will always emerge when you are doing multiplication of binomials. This idea of saying I have two things and two things together. So 3 and 8 will multiply to 24, and 6 and 4 will multiply to 24. And the same thing over here. 8x squared and negative 3 will multiply to negative 24x squared, and negative 2x times 12x will get me negative 24x squared. And that's going to happen with any two sets of two numbers that you choose, and however you want to reorganize them. Now, this is a beautiful pattern, but why is it of interest to us? Well, because it's going to allow us to do this process in reverse very, very easily. So let's take a moment and look. If I wanted to instead discover if the polynomial 3x squared minus 2x minus 1 could be written as a rectangle, we encounter a little bit of difficulty. So notice we're going to try to draw our rectangle. As we try to place things in our rectangle, because this is now all of the components for my rectangle, there's no length and width that I have, no parentheses, so we're talking about things inside the rectangle now. I know for certain that I will have my 3x squares always go here, because that's where my x squares will be in this kind of model, and they don't appear in any other box. Now for the units, I know my -1 is going to go in the bottom right, because again, just like the one up here, there are no units, there are no just numbers without variables in any box other than the bottom right. But what about my -2x? Where does that one go? Well, in the box up here, you can see that there are actually two different places, this one down here and this one down here, that split up our middle part, right? Because if I was to say that all of this comes out to be 8x squares, 10x's, and -3. Where is the 10x's? It's the total of the 12x's in the top right and the -2x's in the bottom left. So it's like we've split the 10x into a certain amount in the top right and bottom left. How do we split this one? Well, we don't know. That's the puzzle that keeps us from being able to form these rectangles easily. But instead of trying to guess and check and playing with fractions and decimals and negatives, or maybe just splitting things up evenly, let's use the pattern that we saw above. Because after all, what we are looking for are two numbers, a number to go here and a number to go here, so that the multiplication, the product of those two, gets us the exact same thing as the multiplication of these two. So let's take a look. I like to organize my thought process in a bit of an X or diamond pattern for this one, because after all, what I'm looking for are two things that multiply to 3x squared times -1. So that would be -3x squared is the pattern that we're going to get when we multiply the diagonals, -3x squared, and this one will eventually come out to be -3x squared. Okay. But what do I get to work with to create this pattern? I only have -2x's that I still have to make sure I get by the end of this splitting apart. So that would be -2x's. I like to put it at the bottom. And I like to think about what numbers, this number here and this number here, are going to add down to get my -2x, but are going to multiply up to get this pattern. And by asking ourselves for two numbers, we get a nice orderly way of being able to discover the rest of this rectangle. So what's something that multiplies to -3x squared? Well, I know that the x's are always going to work out, so maybe we'll make this even simpler. So we'll take this and actually make this an even simpler exploration. Let's just pay attention to the numbers. Because I need it to multiply up to -3, I need the numbers to multiply to -3 and add to -2. So what's something that multiplies to -3? How about -3 and +1? And then I can check, do those add to -2? They do. So I've now figured out everything I need for my rectangle. I just need to put in here that this one is going to be -3x. This one's going to be +1x. There it is. Let me make that one look a little bit cleaner here. So we've got -3x and a +1x, because in total, these all together were my -2x's. I've just located them into the box, and they match up with the rest of the pattern. So how does our rectangle transform? Our rectangle transforms into, well, what can multiply into 3x squared and an x? Just an x. What can multiply into a 3x squared and a -3x? That would be a 3x. They're our greatest common factors that we're writing on the outside of this rectangle. What multiplies into a 1x and a -1? Well, that would have to be a number 1. And what multiplies into a -3x and a -1? That would have to be a -3. Oh, -1. There we are. So what we're doing in terms of pictures is finding a way to write this entire thing as a rectangle. X minus 1 times 3x plus 1. And that's how you can factor something out. Now that was a nice exploration. Let's find a way to make this one a little bit cleaner. For the next example, let's take a look at doing x squared plus 4x minus 32. So again, we're trying to find out if we can factor this. In other words, if we can write this as a rectangle and describe it by its length and width instead of everything that's inside. So if I was going to try to factor this out, x squared would go here, negative 32 would always go here, and I'm looking for a way to separate my 4x so that part of it is in the top box and part of it is in that bottom box. So how can I organize my thoughts? I'll draw a nice little x here and say that I'm looking for numbers that add up to this 4x and that are going to multiply to the same pattern as x squared times negative 32. But I guess I can ignore the x squared, so that's just going to be 1 times negative 32. That would be negative 32. So what's something that adds to 4 and multiplies to negative 32? That's a bit of a harder problem. So maybe I would like to make a table of factors here, because after all, the multiplication is what's stumping me. So I'm looking for things that multiply to negative 32. What are some things that multiply to negative 32? 1 and 32. I guess I could put the negative here. And then I could think of 2 and 16. I'll put the negative here still. 3 does not work very easily. 4 is going to work. 4 is going to be 4 and 8. I guess I could put the negative here. Oh, and look at that. In fact, isn't negative 4 and 8, aren't those two numbers that multiply to negative 32 but add to 4? I think those are our missing numbers. We'll put negative 4 here and 8 here. And that's exactly what I want to split up over here too. I want to put negative 4x over here, because that's where my x's go, and 8x's right here. So that's my rectangle. That's a rectangle that works very nicely with how I started. What's the length and the width? Well, since this is all groups, I'm really looking for what is the greatest common factor between x squared and 8x. In other words, what multiplies into both x squared and 8x, and that would be just an x. What multiplies into x squared and negative 4x? Again, I think that's going to be just an x. What's something that multiplies into negative 4x and negative 32? Well, I think the biggest number would be a negative 4. And what's something that multiplies into 8x and negative 32? I think that's going to be an 8. So all in all, we can say that this entire thing is really just x minus 4 for the length on top times x plus 8 for the width going down. And that's the exact same expression we have. We found a way to take something that was addition and use multiplication to talk about it instead. So why is this called the AC method? Well, because the standard form of a quadratic is often written like this: ax squared plus bx plus c. And we use standard forms as just kind of like our default go-to for how to describe something. And this is a nice default way of describing a quadratic. We'll put the biggest term in front, and we'll talk about how many that is. So for here, a would be the number 1. B would be the number of x's, and c would be the number of units. So the AC method, in its steps, says 1, take a times c. This is why it's called the AC method. Step 2, take b. That would be the second number that appears, the one next to the x's. 3 would be find two numbers such that they add to b and multiply to a times c. Step 4 would be separate b into these numbers. So what are we talking about in the steps here? Well, really what we're doing in the picture, because again, let's walk through exactly what's happening. Take A times C. All that was recognizing that we're always going to get the pattern when we look at the diagonal here. So this right here is AC. This is the A times C. Take B. What is B? B is the middle number. So that was looking for the amount of material I had to actually work with. That was my 4 right here. Find two numbers such that they add to B and multiply to A times C. That was what we were doing when we were trying to figure out what the question marks were in these parts of our kind of diagram. And then all we're looking for is a way to separate that middle into exactly what we have. Two other parts for our rectangle. Now, for the rest of the factoring, we did it in terms of pictures. Let me show you how we could do all of this in terms of symbols. So let's look at the entire problem again, but this time we're going to do it from a fresh eyes perspective. So it's x squared plus 4x minus 32. Now, if we were going to follow the AC method without any diagrams, here's how it's often expressed in textbooks. First thing first, we're looking for things that are going to multiply to A times C. So it's going to be 1 times 32, that's 32. Oh, 1 times negative 32, negative 32, and then adds to 4. I like to just think about the even, or the positives for right now, things that multiply up to 32. 1 times 32, 2 times 16, 4 times 8, and then remember that it's a negative, so I can choose where to place the negative sign, and I'm going to choose to place it in this combination and make my pattern be negative 4 and 8. Now, in the diagram at this point is where we would start to fill in our rectangle. If we were just using symbols, what we're really doing is just, again, recognizing the perfect way to separate that middle term, that B term. So notice all we've done in this step is just choose a way to separate 4x into something that has the same meaning and a different perspective. But the advantage of this is that now we're able to look at it in terms of its groups. Now, again, in terms of the rectangle, what we would then do is look for things that multiply to, something here and put it on top as the greatest common factor. If we were doing it just in the symbols, it's the exact same thing. But now what we're doing is factoring by grouping. So when we say what's something that multiplies into both, we're really just trying to factor away. And the thing that is common as a factor for x squared and negative 4x is just the x. So I can write that on the outside. For the next one, the common factor, the greatest common factor for 8x and negative 32 would be 8. So I'll write that on the outside and then pull out everything I can. And then from there, we just recognize that I have this x minus 4 affecting both the x and the 8. So that would be x plus 8, both being multiplied by x minus 4. And we can be done just like that. That would be a way of factoring out the original quadratic. But again, all we're really doing is, in terms of the picture, starting off where we have x squared and negative 32. We're looking for a way to split up the 4x, so we'll do the exact same kind of pattern exploration and find out that what we need to do is put a negative 4x here and an 8x here. And we were looking for ways to multiply back in. That's what we were doing here by factor by grouping, is that we're just recognizing that a rectangle has these groups within it, that there is an x amount of 8 or an 8 amount of x and an x amount of negative 4 or a negative 4 amount of x. And when we factor away, we're recognizing that the side lengths, x minus 4, is just simply a common thing that is used for grouping. The same thing is true for the x plus 8. It's just a common grouping. And this is why I like to do the AC method. So if you want to go back to your notes and add in, we could probably say that if we wanted to play with just the symbols, what we are doing after we separate the b into these numbers is really just factor by grouping, which is no different than just drawing a rectangle and looking for the numbers on the outside that would make the same amount of groups on the inside.